In the previous video in this series, we learned about the factors that affect SN1 reactions and compared those with the factors that affect SN2 reactions. That material that we covered is summarized here on the screen. In this video, we will see how these ideas might be tested on your exams. Please pause the video and try this problem. Now we'll discuss it together. Well, we know the way to compare carbocations is by classifying them as primary, secondary, or tertiary. So let's do that. This looks like a primary carbocation. Remember, we're focusing on this carbon because that's the one with the positive charge. This carbon is connected to one carbon chain, primary. This would be a tertiary carbocation because this carbon is attached to three carbon chains. But we should also immediately notice that it's resonance stabilized. So this is tertiary with resonance. Here's another tertiary carbocation. This carbon is connected to three carbon chains, but there's no resonance here. There's no lone pairs or pi bonds that can shift towards the positive charge. And this is what we would call not a primary, but a methyl carbocation, because this carbon is attached to zero other carbon chains. So now to rank these in order of stability, we know that tertiary should be the most stable. Tertiary is the most stable because we know that each of these electron-donating carbon chains helps to stabilize the electron-poor positive charge. Then after tertiary, there should be primary, and then less stable would be the methyl group. I'm arranging the compounds like this from high to low because least stable also means highest energy, and most stable means lowest energy. So for me, it's intuitive to put the most stable low on the page because those are low energy, and the least stable high on the page because those are high energy. Now, how about the tertiary with resonance? Well, we know that the resonance will make this even more stable than an ordinary tertiary. Having the resonance will make this even more stable than an ordinary tertiary carbocation. So I'll write tertiary with resonance at the very bottom of this list for the most stable. Now we can rank these. We know that we want to use the ranking of 1 for the least stable. So this would be a ranking of 1, 2, 3, and then a ranking of 4 for the most stable. And now we can write down our answer. The methyl has a ranking of 1, least stable. Then the primary has a ranking of 2. The tertiary has a ranking of 3, and the tertiary with resonance has a ranking of 4. So here's our answer. That problem gave us a chance to practice what we've learned about how to rank stability of carbocations. We know that substitution with carbon chains stabilizes carbocations because carbon chains are electron donating, but we also learned that resonance can also stabilize carbocations. For simplicity, I didn't specifically include resonance stabilized tertiary carbocations in this list, but it should be obvious that a resonance stabilized tertiary carbocation would be even more stable than an ordinary tertiary carbocation. It's easy to get confused and make careless mistakes on these ranking problems when there's multiple things to compare. So one thing you can do is notice how I tried to be very clear in my work about which was the least stable end of my work and which was the most stable. Write things down to help you avoid getting confused. Pay careful attention to whether you're supposed to rank things in order of increasing or decreasing stability. And just double check when you're done to make sure you didn't make any careless mistakes. 1 is supposed to be least stable. Well, yeah, methyl is the least stable carbocation. Then primary, then tertiary with resonance. Just double check your work on this type of problem because it's easy to make careless mistakes when you're ranking multiple different options. Again, write down notes to yourself to make your notes more helpful. If I hadn't written down which end here was the least stable and which was the most stable, it would be much easier for me to make a careless mistake. Just writing down these little notes makes it much less likely that I'll make a careless mistake. All right, so remember that when you're comparing carbocations, we classify them in terms of primary, secondary, tertiary, and methyl, but we also classify them in terms of whether there's resonance. Here's a question we haven't discussed in these videos. Can you give an example of a savolysis reaction? Well, we haven't discussed that yet, so I'll just tell you the answer. SN1 reactions that use the water or alcohol as the nucleophile are an important example of savolysis. At this point in the course, if we use the term savolysis, basically that means an SN1 reaction using water or alcohol as the nucleophile. Can you see why this is a logical term? It's logical that it has solvo in the name. That refers to the solvent. Remember that water and alcohol are used as solvents. So it makes sense that this has solvo in the name to refer to the solvent. And do you know what lysis means? You should know that lysis means breaking. Well, an SN1 reaction that uses water or alcohol as the nucleophile uses the water or alcohol to break apart the substrate. Here's an example we saw in the previous video. This is an SN1 reaction using water as the nucleophile. And do you see how we're using the water to break this substrate into pieces? We're using this to form a permanent separation between the alpha carbon and the leaving group. At the beginning of the reaction, the alpha carbon is attached to the leaving group, and by the end of the reaction, the alpha carbon is no longer attached to the leaving group because the water has interposed, so to speak. So this would be an example of a solvolysis, using the solvent to break apart the substrate. So again, you should know that at this point in the course, the word solvolysis refers to SN1 reactions that use water or alcohol solvent as the nucleophile. I'm covering this now simply because this is a term that you might possibly see used by your professor on exams, and this was a convenient time to cover that term. Please pause the video and try this problem. Now we can discuss. I guess it would help to put in some numbers. For simplicity, I guess it's not necessary to number these other carbons in this molecule. And I suppose it would help to identify the alpha carbon. The alpha carbon is the carbon attached to the leaving group. So carbon 2 is the alpha carbon in this picture. Carbon 5 is the alpha carbon in this picture. It would help to identify the mechanism. Well, we just learned what savolysis is. We just learned that savolysis is an SN1 reaction that uses the water or alcohol solvent as the nucleophile. And notice here we do have a water solvent, so it makes sense that we could use water solvent for an SN1 savolysis reaction. So notice that when you see this term, that's basically a code that says SN1 reaction. So we want to know, basically this is asking which of these reactions will be the faster SN1 reaction. Well, to compare these, they both have the same leaving group. So we can't compare them based on leaving group because that's the same. And they both have the same nucleophile, water. When you're making a comparison, you have to look for something that's different between the molecules. Well, the thing that's different here is the alpha carbons. And we compare alpha carbons by focusing on primary, secondary, or tertiary. Alpha carbon in compound A is tertiary, because carbon 2 is attached to 3 other carbon chains. The alpha carbon in compound B is secondary, because carbon 5 is attached to 2 carbon chains, one that proceeds clockwise around the ring and one that proceeds counterclockwise around the ring. Well, we've learned that tertiary alpha carbons are better than secondary for SN1. We've learned that tertiary alpha carbons are better than secondary alpha carbons for SN1. So here's our answer. Substrate A undergoes the faster SN1 savolysis reaction. Now this wouldn't be a full credit answer because we haven't explained why. So you'd have to articulate why this is faster. So here's a better answer that explains that substrate A is better for SN1 because it has a tertiary alpha carbon, which is better for SN1 than a secondary alpha carbon. This still might not be 100% credit because we still could go deeper into explaining why. Why is a tertiary alpha carbon better for SN1 than a secondary? How would you explain that? So here's a better answer that explains that a tertiary alpha carbon is better for SN1 than a secondary because a tertiary carbocation is more stable than a secondary carbocation. I think this would be a full credit answer. This would be a full credit answer. But even so, just for our own understanding, can you explain why a tertiary carbocation is more stable than a secondary? So here's even more detail about why tertiary carbocations are more stable. It's because carbocations have too few electrons, and carbon chains help to stabilize that because they are electron donating. A tertiary carbocation has one extra carbon chain that a secondary doesn't, and that extra carbon chain helps to stabilize the carbocation by donating electrons to the carbocation. Here there are 3 carbon chains surrounding the carbocation that can stabilize the carbocation by donating electrons to it. Here there are only 2 carbon chains surrounding the carbocation that could stabilize the carbocation by donating electrons to it. Okay, this is probably a lot more detail than you would need for a full credit on an exam problem. Probably this would be enough for full credit, but it's good to go through all the details to make sure you actually have understanding of the material. Notice that it would be hard to get this problem correct if you didn't know what the term savolysis means. So make sure that you have memorized that savolysis refers to SN1 reactions using water and alcohol solvents. At least that's the main use of the term at this point in the course. So earlier we have learned this pattern for which alpha carbons are best for SN1. Tertiary alpha carbons are better than secondary alpha carbons for SN1. And this problem is an example of how that idea could be tested on an exam. Please pause the video and try this problem. Now let's discuss. We could start by numbering the carbons. Normally, it would be a mistake to use the same numbers for different compounds. Normally, I wouldn't use the same numbers for different compounds. But since these compounds are so similar, and since our goal is to compare the compounds, since our goal is to compare these, I think on this problem it will be helpful to use similar numbers for the 2 compounds. Okay, so now we can start comparing these. I guess we can identify some roles. We would expect neutral bromine to play the role of leaving group. We would expect this alcohol to play the role of nucleophile. Now, do you understand what the ET means? You should know that ET is an abbreviation for ethyl. So the ET just stands for an ethyl group. So this is just an alcohol that has an ethyl group, ethyl alcohol. So this is just a normal alcohol solvent that has 2 carbons. And do you know what the triangle symbol means? You should know that this triangle symbol in chemistry stands for heat. So this is a reaction where we are heating up the starting materials. It turns out that that's not going to play any important role in our solution to the problem. We should label our alpha carbon. The alpha carbon in this picture is carbon 4. And in this picture, the alpha carbon is carbon 3 because those are the carbons that are attached to the leaving group. Now we should determine the mechanism. Should we use the table? Should we use the table to determine the mechanism? No, because the problem told us the mechanism. If the problem tells you the mechanism, then you don't use the table. Instead, you use the mechanism from the problem. So we know that both of these reactions will be occurring through a SN1 reaction because the problem told us so. I applied that same idea to this problem. I didn't use the table to determine the mechanism here. I just said it was SN1 because the problem mentioned savolysis, and we know that's SN1. Now, to determine which of these is faster, we have to look for some difference between these 2 compounds. It's useless to compare the leaving groups because they have the same leaving groups. It's useless to compare the nucleophiles because they have the same nucleophiles. But they do have different alpha carbons. Here the alpha carbon is carbon 4. Here the alpha carbon is carbon 3. So we should compare those alpha carbons and decide which is better for SN1. Well, we'll start by checking for primary, secondary, or tertiary. Carbon 4 is a secondary alpha carbon because it's attached to 2 carbon chains. But carbon 3 is also a secondary alpha carbon because carbon 3 is also attached to 2 carbon chains. Well, that doesn't help us because remember we're trying to find some way in which these compounds are different. Well, they both have alpha carbons that are secondary, so that's not a difference between them. So how are the alpha carbons different? It might be obvious to you. It might be obvious to you how the alpha carbons are different. But if not, it would be helpful to start going through the mechanism. So let's start going through the mechanism here and see if that helps us to see how these compounds are different. It's an SN1, and we know that the first step for an SN1 is for the leaving group to leave. Remember, the most important thing is to change charges. When the alpha carbon loses its bond, it changes from neutral to positive. So make sure you show the positive carbocations. Now, both of these carbocations are secondary, but we know that something else that influences a carbocation besides its substitution is whether there's any resonance. And I hope that you can recognize that there are no other resonance structures for this intermediate, but there is another resonance structure for this intermediate. There's another resonance structure for this intermediate that we can get by using electron pushing arrows that look like this. Notice that based on this electron pushing arrow, carbon 1 loses electrons to become positive, and carbon 3 gains electrons to become neutral. So you can see this carbocation is resonance stabilized because the positive charge is spread out between carbon 1 and carbon 3. This carbocation is not resonance stabilized. It's too far from the pi electrons to participate in resonance with those pi electrons. Carbon 4 is too far from these pi electrons to participate in any resonance with the pi electrons. Resonance structures involve the movement of pi electrons. So here would be a good answer. Notice that it's not enough to say that reaction B is faster. You must justify your answer for full credit. This would be a good justification. I would encourage you on this problem to actually draw the carbocations and draw these two resonance structures as part of your explanation. That might be more detail than the professor requires, but the professor might appreciate that detail, and it helps you to make sure that you actually understand this material. So what I have written down here on the screen would form a good explanation for this problem. So notice that it can be helpful to draw part of the mechanism, even if the question doesn't specifically require it. It helped us to draw the first step of this mechanism so we could form the carbocation and then show that this carbocation has resonance and this one does not. Earlier we learned that substitution stabilizes carbocations, but we also learned that resonance stabilizes carbocations. And this problem gave us a chance to practice the idea that resonance stabilizes a carbocation. A lot of students would not get this correct because most students don't even think about resonance unless they see the word resonance in the problem. Notice that this problem never mentioned the word resonance. We had to think to use the concept of resonance on this problem, even though it wasn't mentioned in the problem. Look for opportunities to apply resonance when you're solving problems. Remember, it would help here to know what the ET stands for. ET stands for an ethyl group. So this is ethyl alcohol. Remember, the triangle here stands for heat. This is a reaction. These reactions took place in the presence of heat. That didn't turn out to have any significant impact on how we solved the problem. By the way, here's a table that you might find useful in your organic chemistry class. Oftentimes in Ochem, you'll see exam problems that ask you to explain something, like the previous problem. So what factors should you consider for trying to explain things? So this is a checklist that you should consider when you have to explain something in organic chemistry. Of course, the most important thing to think about is formal charges. First, think about formal charges. But maybe the second most important thing to think about is resonance. Think about whether resonance plays a role. Remember that if resonance does play a role in a reaction, it's usually the most important factor. Steric hindrance plays an important role in organic chemistry. Also sometimes electronegativity, delta charges, molecular geometry. So it's useful to have this checklist that you can run through in your head if you're given a question like this previous one where you have to explain or justify something. Obviously, this is far from complete. There are many other factors. There are many other factors that might sometimes be important in Ochem. These are just some of the most important factors that occur to me right now. So I suggest that this would be a useful table to have in your notes. If you see an Ochem problem where you need to explain why something happened or didn't happen, it's useful to run through these factors and ask whether any of them are applicable for the problem. Obviously, for the problem we just worked with, the key factor was that one structure had resonance in the carbocation and the other structure did not have resonance in the carbocation. Remember that when you're comparing two structures or two reactions, you have to look for a way that they're different from each other. This is a variety of different ways in which two reactions or molecules could be different from each other. Please pause the video and try this problem. Now we'll discuss. We could start by numbering the carbons. In this case, it makes sense to give different numbers to the two different molecules. Then I guess we can start by identifying our roles. We would expect the chlorine to be our leaving group and the water to be our nucleophile. Carbon 7 here will be the alpha carbon, and carbon 10 here will be the alpha carbon, because those are the carbons attached to the leaving group. We need to identify the mechanism, but we're not going to use the table. We won't use the table for identifying the mechanism. Instead, the problem tells us. The problem tells us that this mechanism is an SN1 mechanism. Now we look for a difference between these two reactions. Well, they have the same nucleophile and the same leaving group, so let's compare the alpha carbons. The alpha carbon for reaction A is a primary alpha carbon, and the alpha carbon for reaction B is a secondary alpha carbon. So you might think that reaction B will be better for SN1 because we know that secondary alpha carbons are better than primary alpha carbons for SN1. But remember, we've learned that there's another factor that affects the alpha carbon. It's not just whether it's primary, secondary, or tertiary. You also have to check whether the carbocation has any resonance stabilization. So let's not end the problem too soon. Let's go further and see if either carbocation would have resonance stabilization. So the mechanism for the first step of the reaction would look like this, and we can draw the carbocation intermediate. Remember that after the alpha carbon loses electrons, it forms a carbocation intermediate. Now you might think that a secondary carbocation is better than a primary, but remember we also have to check for resonance. And this carbocation is close enough to these pi electrons for there to be resonance structures. Can you draw the electron pushing arrows for that? So here's what the electron pushing arrow would look like. By the way, notice that this arrow is wrong. This arrow is wrong. You should not draw the arrow pointing directly to carbon 7. Instead, it should point to the bond between 1 and 7, because that's how you show that you're forming a pi bond. The way to show that you're forming a pi bond is to show the arrowhead pointing between the two atoms. So that gives us another resonance structure. Remember to change two charges. The atom at the end of the arrow, carbon 7, changes its charge, and the atom that loses electrons at the beginning of the arrow, carbon 6, changes its charge. So clearly this carbocation is resonance stabilized. In fact, there's even two more resonance structures. Here are all the electron pushing arrows to show all those different resonance structures. Notice that each electron pushing arrow, the arrowhead is pointing to a bond. Arrowhead pointing to a bond. Arrowhead pointing to a bond. Because that's how you draw an electron pushing arrow that shows the formation of a pi bond. Okay, so clearly this carbocation is far more stabilized than an ordinary primary carbocation. This is an extremely stable carbocation because it's spread between 1, 2, 3, 4 different resonance structures. The positive charge is spread between carbon 7, carbon 6, carbon 4, and carbon 2. That's going to be far more stable than this carbocation, which is concentrated just on carbon 10. There are no additional resonance structures for this carbocation because there are no pi electrons to move around in this molecule. Remember that resonance structures have to involve the movement of pi electrons. To put that in more usable terms, resonance structures involve the movement of pi bonds and lone pairs. Resonance structures involve the movement of pi bonds and lone pairs, and we don't have an opportunity for either of those things here. All right, so it should be clear that reaction A will be faster because it forms the more stable carbocation. Here's our answer. Reaction A is faster. Remember, you must justify your answer for full credit. So reaction A is faster because this alpha carbon forms a resonance-stabilized carbocation, and this alpha carbon forms a carbocation with no resonance stabilization. And it might help you to get the credit if you draw at least one of these resonance structures. So it might definitely help here to draw the first step of the mechanism to show the carbocation, and then draw at least one of these resonance structures to show the resonance stabilization for reaction A that's lacking with reaction B. Notice there's a trap here, but a lot of students thought that reaction B would be faster because it has a secondary alpha carbon, whereas this one is primary. You also have to consider resonance, and just as a problem-solving tactic, when a problem involves resonance, it's usually the most important factor in the problem. On introductory Ochem exam problems, when the problem involves resonance, that's usually the most important factor. So the resonance here is more important than primary versus secondary. We learned earlier that a primary alpha carbon that forms a resonance-stabilized, resonance-stabilized carbocation is more stable than a secondary alpha carbon. And this particular primary carbocation is especially stable because it forms not just one additional resonance structure, but 3 additional resonance structures. Notice again that the problem never mentioned the word resonance. It was up to us to think about resonance on this problem, although it wasn't specifically mentioned. Resonance is a factor that you should always be on the lookout for in Ochem problems. Remember that this problem involved an SN1 mechanism. And what is the big obstacle to SN1? The big obstacle for SN1 is stabilizing the carbocation. So for that problem, the SN1 reaction that was faster was the SN1 reaction that allowed a more stable carbocation. When thinking about SN1, focus especially on the big obstacle to SN1, stabilizing the carbocation. You can stabilize the carbocation with a more substituted alpha carbon, but you can also stabilize the carbocation with resonance stabilization. Please pause the video and try this problem. Now we can discuss. We can start by numbering the carbons. Normally I would give different numbers to these two different molecules, but because these two molecules are so similar and because our whole goal is to compare these two molecules, I think here it's helpful to give similar numbers to the two compounds. We don't need to look for ionic bonds because the ionic bond was already drawn in for us with the formal charges. And we don't need to use our table to determine the mechanism because the problem told us the mechanism. We don't use our table here to figure out the mechanism because the problem told us the mechanism. So to figure out which of these SN2s will be faster, we have to look for a way that the starting materials are different in these two reactions. I guess I'll go ahead and label the roles. We expect that this O- will be the nucleophile because of its negative charge. This will be a solvent that doesn't participate in the reaction. We expect the Br will be our leaving group. Neutral bromine is a good leaving group, which makes carbon 3 our alpha carbon. Carbon 3 will have a delta positive and be the electrophile. Now it doesn't help to compare the leaving groups for this problem because both leaving groups are the same, neutral bromine. It doesn't help to compare the nucleophiles because both nucleophiles are the same, CH3O-. So it looks like we'd like to compare the alpha carbons, but it looks like the alpha carbons are also very similar. Both of these alpha carbons are primary. Here's a primary alpha carbon, and here's another primary alpha carbon. In fact, really the only difference here is at carbon 2. The only way these starting materials are different is at carbon 2, so clearly we have to compare which of these carbon 2s is better for an SN2 reaction. Well, what is the big obstacle for an SN2 reaction. You should have memorized that the big obstacle for SN2 is steric hindrance. So we should be asking whether we can use steric hindrance to explain why one of these reactions might be faster than the other. Well, isn't it clear that this carbon-2 is going to provide more steric hindrance than this one? Carbon-2 in this picture is tertiary. Carbon-2 in this picture is a tertiary carbon. But in this picture, carbon-2 is secondary. Well, since there's fewer carbon chains around carbon-2 in this picture, there's less likelihood that these carbon chains can get in the way and block the nucleophile from attacking carbon-3. So, for example, in this picture, it's possible that sometimes carbon-1 is going to rotate into a position where it blocks carbon-3 and makes it difficult for the nucleophile to attack carbon-3. On the other hand, in other cases, carbon-1 might be rotated away from carbon-3 so that it doesn't block carbon-3. But in this picture, there are two methyl groups that could rotate into a position to block carbon-3. Methyl group 4 could rotate into a position to block carbon-3, and when methyl group 4 is not rotated into that position, methyl group 1 could rotate into a position to block carbon-3. So with those two separate methyl groups that could block carbon-3, there's more steric hindrance in this molecule and less in this molecule. Of course, we know that we primarily focus on steric hindrance from the alpha carbon. Usually we focus primarily on steric hindrance from the alpha carbon, but steric hindrance from the next door carbon can also sometimes play a role, and clearly that's what we need to focus on for this problem. So here's our logic. This starting material has less steric hindrance at carbon-2 that could block the nucleophile from attacking carbon-3. And therefore, we have a faster SN2 in this case. And this molecule has more steric hindrance at carbon-2 that could block the nucleophile from attacking carbon-3, which gives this reaction a slower SN2 reaction. Remember, the big obstacle to SN2 reactions is steric hindrance. So here's our answer. Reaction B will have the faster SN2 rate, because for reaction B, carbon-2 has less steric hindrance that can block the nucleophile from attacking carbon-3. Remember, you have to justify your answer to get full credit for this problem. By the way, there's another way to describe this situation. We know that carbon-3, which is attached to the leaving group, is called the alpha carbon. What's a good name for carbon-2? Well, a good name for carbon-2 would be the beta carbon. The carbon that's attached to the alpha carbon can be called the beta carbon. So we can call carbon-2 the beta carbon because it's attached to the alpha carbon. Carbon-2 is the beta carbon because it's attached to the alpha carbon. So then we could say here that it's the beta carbon that's tertiary in this picture and the beta carbon that's secondary in this picture. In this picture, the beta carbon is tertiary, whereas in this picture, the beta carbon is secondary. And that gives us another way to describe our reasoning. Now we can say that reaction B is faster because for reaction B, the beta carbon has less steric hindrance that could block the nucleophile from attacking the alpha carbon. So this would be a good way to phrase our answer to the question. Of course, this would also be acceptable. So either of these two ways of phrasing the answer would be acceptable. So we've learned that the alpha carbon is the carbon that's attached to the leaving group, and the carbon that's attached to the alpha carbon can be called the beta carbon. There are some other topics in Ochem where that's useful terminology. In the past, we've generally focused the most on steric hindrance from the alpha carbon. Usually we focus most on steric hindrance from the alpha carbon, but steric hindrance from other carbons, such as the beta carbon, can also sometimes play a role in affecting the rate of a reaction. Now, the main purpose of this video series is to focus on SN1 reactions, but when you take your exam, you're going to have to move back and forth between SN1 reactions and SN2 reactions and other types of reactions. So it's important sometimes in these videos not just to talk about SN1, but also to switch gears and make sure that we can switch gears to answering questions about other types of mechanisms. So we need to be able to go back and forth between questions about SN1 reactions and questions like this one that's about SN2. Remember that the big obstacle to an SN1 reaction is stabilizing the carbocation. But the big obstacle to an SN2 reaction is steric hindrance that blocks the nucleophile from joining the alpha carbon. So when we worked on this problem that involved an SN1 mechanism, we focused on which reaction would have a more stabilized carbocation intermediate. Because the big obstacle to SN1 is stabilizing the carbocation. But then when we switched gears and shifted to this problem, which was dealing with an SN2 mechanism, here we focused on which starting material would have less steric hindrance that could block the nucleophile, because we know that the big obstacle for SN2 is steric hindrance that blocks the nucleophile. So make sure you pay close attention to whether each problem is about SN1 or SN2 so that you can switch gears in your mind between those two different ways of thinking about the factors that can affect mechanisms. Please pause the video and try this problem. Now let's discuss. We can start by numbering the carbons. Because this molecule and this molecule are identical, and because our goal is to compare them, I've given them the same numbers. There are no ionic bonds in this reaction, and we're told the mechanism. We're not going to use the table. We won't use the table for the mechanism because the problem tells us that the mechanism will be SN1. Label some roles. There are no negative atoms to act like nucleophiles, so we can use neutral atoms as nucleophiles. A neutral oxygen has a lone pair and can be used as a nucleophile. A neutral sulfur also has a lone pair and can also be used as a nucleophile. In this video series, we've mainly been using neutral oxygen as our neutral nucleophile. But earlier we've seen that there are other neutral atoms that can also function as nucleophiles because of their lone pairs: nitrogen, sulfur, and phosphorus. So a neutral sulfur with its lone pair can act like a nucleophile. We can identify the neutral iodide as the leaving group, and that allows us to identify our alpha carbon as carbon 3. Now, to compare these reactions, we have to look for the difference between the reactions. It's useless to compare the leaving groups because they both have the same leaving group. It's useless to compare the alpha carbons because the alpha carbons are identical. They're both secondary alpha carbons. So what is the difference? The difference is the nucleophiles. Here we have the neutral sulfur as a nucleophile, and here we have neutral oxygen as a nucleophile. Now you should know that neutral oxygen is a poor nucleophile. And you should know that neutral sulfur is a good nucleophile. How? How should you know that? You should know that because you should have memorized this table. You should have memorized that the neutral oxygen in an alcohol is a poor nucleophile. And you should have memorized that neutral sulfur is a good nucleophile. So from memorizing the table, we know that this is a good nucleophile and this is a poor nucleophile. Notice that there are some neutral atoms that are good nucleophiles. Most good nucleophiles have negative formal charges, but there are a few neutral atoms that can also be good nucleophiles. Okay, so reaction A has the better nucleophile. Does that mean that reaction A will occur more quickly? Well, not so fast. We have to ask, does nucleophile quality matter for an SN1 reaction? Does nucleophile quality matter for an SN1 reaction? Remember, we learned earlier that nucleophile quality does not matter for an SN1 reaction. That might seem strange, but remember the reason for that is that the nucleophile doesn't participate in the rate determining step. Here's the rate determining step for SN1, and you can see that the nucleophile is playing no role in this rate determining step. Well, remember, anything that does not affect the rate determining step will not affect the rate of the reaction. So improving the nucleophile quality does not increase the rate of an SN1 reaction because the nucleophile doesn't participate in the rate determining step. So here's our answer. Both of these SN1 reactions occur at the same rate. Remember, for full credit, we have to justify our answer. While reaction A does have a better nucleophile, but that doesn't matter for SN1, nucleophile quality doesn't affect the rate for SN1 because the nucleophile doesn't participate in the rate determining step for SN1. Did you get this problem right? This problem is a good test of whether you were really understanding the material about factors that affect SN1 reactions that we covered in the previous video. Finally, by the way, what does this triangle mean? Well, you should know that the triangle means heat. These are reactions where we're adding heat to the starting materials. Notice that didn't really have any effect on how we solved the problem. Please pause the video and try this problem. Now let's discuss the solution. We can start by numbering all the carbons. We can identify the mechanism. Now we don't use our table for the mechanism. The problem tells us the mechanism. Remember, don't use the table for the mechanism if the problem tells you the mechanism. Here we're focusing on SN2. We can identify our roles. Neutral oxygen will be our nucleophile here, and neutral sulfur will be our nucleophile here. Neutral sulfur and neutral oxygen can both be nucleophiles because of their lone pairs. Our leaving group will be the neutral iodide, and therefore carbon 3 will be our alpha carbon. Now we need to look for a difference between these two reactions. Well, the leaving groups aren't different. The leaving groups are the same. The alpha carbons aren't different. They're both primary alpha carbons. So we have to focus on the difference in the nucleophiles. And we should know that sulfur is a good nucleophile. Whereas, I should say, neutral sulfur is a good nucleophile, whereas neutral oxygen is a poor nucleophile. Remember, the most important thing to focus on is formal charges. So you shouldn't say that you're comparing sulfur and oxygen. You should say that you're comparing neutral sulfur and neutral oxygen. Always focus on the formal charge. How do we know that neutral sulfur is a good nucleophile and neutral oxygen is a poor nucleophile? Well, we discussed that same issue in the previous problem. In the previous problem, we saw that we can use the table to remind ourselves that neutral oxygen, such as in an alcohol, is a poor nucleophile, and neutral sulfur is a good nucleophile. You should have that information from the table memorized. Now, does nucleophile quality affect the rate of an SN2 reaction? Well, yes, we've learned that nucleophile quality does affect the rate for SN2. In the previous video, we learned that nucleophile quality does matter for the rate of an SN2 reaction. Why? Because the nucleophile participates in the rate determining step for SN2. You can see that the nucleophile does participate in the rate determining step for SN2, so having a better nucleophile allows an SN2 reaction to proceed more quickly. So here is our answer. Reaction A will be faster for SN2 because reaction A has a better nucleophile than reaction B. Nucleophile quality matters for SN2 because the nucleophile participates in the rate determining step for SN2. Now, this might not be a full credit answer because we haven't explained why neutral sulfur is a better nucleophile than neutral oxygen. the professor might want you to explain why this neutral sulfur is a better nucleophile than neutral oxygen to really justify your answer. Well, I'm not going to get into those details in this video series. Hopefully, maybe later I can make another video series where I can explain how to rank, how to explain nucleophile quality between different atoms. I will include a brief explanation for why neutral sulfur is a better nucleophile than neutral oxygen in the solutions document for this problem. So based on what we've talked about so far, we can only give this answer, which might not be full credit. But at least here we've practiced the material that we have covered in this video series. From our table, we do know that neutral sulfur is a better nucleophile than neutral oxygen, but we haven't yet given an explanation for why that is. Well, it's important to carefully compare this problem that we just completed with the previous problem. These problems were very similar, but they still had quite different answers. And that shows that nucleophile quality has a much different effect on an SN1 reaction than on an SN2. Nucleophile quality does not affect the rate for SN1, but nucleophile quality does affect the rate for SN2. Nucleophile quality does not matter for an SN1 reaction because the nucleophile does not participate in the rate-determining step for SN1, but nucleophile quality does matter for SN2 because the nucleophile does participate in the rate-determining step for SN2. So one important lesson here is that, again, you have to be able to keep switching gears back and forth on your exam between SN1 mechanisms, SN2 mechanisms, and other mechanisms. Don't assume that any particular problem is about SN1 or SN2. Study the problem to determine the mechanism. In these problems, the problem told you the mechanism. So in these cases, pay close attention to the mechanism that you are given in the problem, because that's going to have a big effect on your answer. Please pause the video and try this problem. Now here's the solution. We can start by numbering the carbons. There are no ionic bonds. These are covalent bonds because hydrogen is a non-metal, and sulfur and oxygen are non-metals, so there's no formal charges. We can use these neutral atoms as the nucleophiles. Neutral oxygen can be used as a nucleophile, and neutral sulfur can also be used as a nucleophile because both of them have lone pairs to donate. We expect that we're going to use the neutral chlorine as our leaving group. That will make carbon 1 into the alpha carbon. So we see that we have a tertiary alpha carbon in both cases. Carbon 1 is tertiary, attached to 3 carbon chains, carbon 6, carbon 5, and carbon 2, a tertiary alpha carbon. We have to choose the mechanism. Well, the problem here does not tell us the mechanism, so we have to use the table to figure out the mechanism. We're in the bottom row of the table because we have a tertiary alpha carbon. Now, in reaction A, we're using neutral sulfur as our nucleophile. That puts us in the middle column, and that means we would be in this cell of the table. On the other hand, for reaction B, we're using the neutral oxygen in water as the nucleophile. That would put us in this left-hand column, which would mean we're using this cell. But notice that in both cases, the same mechanisms are predicted. So the table predicts the same mechanisms for reaction A and reaction B. And we expect that this is going to be a substitution reaction, not elimination. You can see it really is substitution because we're substituting the sulfur nucleophile for the chlorine. From the product that was drawn for you here, you can see the sulfur nucleophile has been substituted for the chlorine. And in this case, you can see that the oxygen nucleophile is being substituted for the chlorine. Notice that on this problem, they drew the products for us. Remember that after this neutral nucleophile attacks, it's going to have a positive formal charge, which it can get rid of by losing a proton. That's why this oxygen has one fewer proton than this one. And again, after this neutral nucleophile attacks, it'll have a positive formal charge, which it can get rid of by losing a proton. That's why this sulfur has one fewer proton than this one does. So it doesn't look like we're using the E1 mechanism here. This looks like a substitution mechanism based on the products. So in both cases, we expect we're getting a SN1 reaction. The table tells us the mechanism will be SN1 rather than SN2. Again, for reaction A, we're in the bottom row for a tertiary alpha carbon, and neutral sulfur puts us in the middle column. That puts us in this cell with an SN1 mechanism. All right, now we have to look for some difference between these two reactions. It doesn't help to compare the leaving groups because the leaving groups are the same. It doesn't help to compare the alpha carbons because the alpha carbons are the same. They're both tertiary. We have to compare the nucleophiles. And we know that this neutral sulfur is a good nucleophile. Neutral sulfur is in this middle column for a good nucleophile. Whereas the neutral oxygen in water is in this left-hand column, and we've learned that that makes it a poor nucleophile. So our first instinct might be that reaction A will be faster because it has a better nucleophile. But wait, does nucleophile quality matter for an SN1 reaction? No. We've learned that nucleophile quality does not matter for an SN1 reaction because the nucleophile does not participate in the rate-determining step for an SN1 reaction. Nucleophile quality does not matter for an SN1 reaction. So we expect that even though reaction A has a better nucleophile than reaction B, reaction A will occur at the same rate as reaction B because the nucleophile quality doesn't affect the rate for SN1. So here's our answer. Both reactions occur at the same rate. Make sure you justify your answer. Reaction A has a better nucleophile, but that's not going to affect the rate for this SN1 reaction because the nucleophile does not participate in the rate-determining step for SN1. Well, this problem was quite similar to the two previous problems that we just did previously in this video. Here's the difference. For this problem, we had to use the table to determine the mechanism. This problem didn't tell us the mechanism, so we had to use the table to determine that the mechanism was SN1. For the two previous problems, the problem told us the mechanism. This problem told us the mechanism was SN1. This problem told us the mechanism was SN2. So we didn't have to use the table to determine the mechanism for these two problems. But this last problem did not tell us the mechanism, so we did have to use the table to determine the mechanism. That was very important, right? That was very important because the answer to this type of question is completely different for an SN1 problem and for an SN2 problem. We know that for an SN1 problem, the nucleophile does not affect the rate. But we also know that for an SN2 problem, the nucleophile would affect the rate. So it was absolutely vital that we used the table to determine the mechanism. If the mechanism had turned out to be SN2, our answer would be quite different for this problem. So for these types of rate problems, always make sure that you're clear what the mechanism is for one of these rate problems. Always make sure that you're clear what the mechanism is, either because the problem told you the mechanism or because you used the table to figure it out. And also notice again, if the problem shows you the products, when the problem shows you the products, that can give you a little bit of an extra clue for figuring out the mechanism. We knew the mechanism here was substitution and not elimination by looking at these products. Please pause the video and try this problem. Now let's discuss the solution. We can start by numbering the carbons. Number all the carbons, including this one. There are no ionic bonds, so there's no formal charges. We can assign some roles. I see a neutral oxygen, which we can use as a nucleophile. Now we have to choose a leaving group. Well, here's a neutral iodide. That's a good candidate for leaving group. But what about this neutral oxygen? Could we use this neutral oxygen as a leaving group? Well, in the first video in this series, we learned that neutral atoms usually are not acceptable leaving groups. Now there are some important exceptions. Neutral chlorine, bromine, and iodide are good leaving groups, and neutral sulfonates are good leaving groups. But other neutral atoms are usually not acceptable leaving groups. That goes for oxygen. Neutral oxygens are usually not acceptable leaving groups. Now there are some important exceptions to that. For example, a neutral oxygen in a sulfonate is a good leaving group, but ordinary neutral oxygens are usually not acceptable leaving groups. The general rule is that neutral atoms are usually not acceptable leaving groups unless you have specifically learned otherwise. So it looks like we should not use this oxygen as a leaving group. Neutral oxygen is not an acceptable leaving group. That means that we would treat carbon 1 as our alpha carbon. That'll be a secondary alpha carbon. Now we can choose our mechanism. With a secondary alpha carbon, we'd be using the middle row of our table. And neutral oxygen in an alcohol is the left-hand column of our table. So we predict an SN1 mechanism. E1 would be minor, but the problem said to draw the substitution products. Remember that the S in SN1 stands for substitution. The E in E1 stands for elimination. So the substitution product would come from SN1 here. Now, again, could we have used this neutral oxygen as the leaving group rather than the neutral iodide? No, because neutral oxygens are generally not good leaving groups. And remember that both SN1 and SN2 mechanisms require a good leaving group. We've seen that the leaving group participates in the rate determining step for both SN1 and for SN2. Therefore, a good leaving group is required for both SN1 and for SN2. So, no, we cannot use this neutral oxygen as our leaving group. And that means that we cannot use carbon 4 as our alpha carbon, and also that we cannot use carbon 6 as our alpha carbon, because they're not connected to a good leaving group. The only good leaving group in this molecule is the iodide, so the only carbon we can use as an alpha carbon for either SN1 or SN2 is carbon 1. So in fact, we'll go with our first instinct and we'll use carbon 1 as our alpha carbon for this SN1 reaction. That's the main issue that I wanted to test with this problem. So what role is this oxygen going to play in this reaction? Well, basically 0 role. The oxygen is just here, I guess, to confuse or distract you. But we're not going to, the oxygen's not going to play any significant role in our reaction. So now we can draw the mechanism for this reaction. The first step for SN1 is that the leaving group leaves the alpha carbon. That forms a carbocation on carbon 1. Now, in our next step, we should do a nucleophile electrophile step. Here is our nucleophile electrophile step. Now, the nucleophile is attacking a trigonal planar carbocation. So the nucleophile can attack from either in front of the page, leaving it on a wedge, or from behind the page, leaving it on a dash. This carbon is a stereocenter, so we get different products depending on whether we attack from in front or from behind the page. Of course, we don't make any changes to the configuration at carbon 4. Since carbon 4 is not participating in the reaction, there's no reason to make any change to the configuration at carbon 4. This stays as a wedge. Most important to get right is this positive charge. The oxygen started neutral and lost electrons, so it has to change to be positive. Now, it looks like we're not done because our main product still has a formal charge. So now we're going to do an acid-base cleanup step. Here are the electron pushing arrows for our acid-base cleanup step. Remember that a base is defined as something that donates electrons to take a proton. This is the right arrow to show a base donating electrons to take a proton. Don't forget to change the charge on this oxygen. It seems like now we are done because now our main products have no formal charge. So probably the professor would be looking for these two products as our answer. These would be considered the main products here that the professor is probably looking for. We can see that this oxygen basically just played the role of a distraction. It didn't play any role in the reaction. We knew it was not going to play a role because neutral oxygen is not an acceptable leaving group. But an SN1 reaction requires an acceptable leaving group. So we can't use this oxygen as our SN1 leaving group. So we can't use carbon 4 as our SN1 alpha carbon. My general advice is that you should make an effort to number all the carbons in all of your pictures. And I notice I didn't follow my own advice there. I numbered this carbon as carbon 7, but I forgot to continue to number carbon 7 in the subsequent pictures. So let's fix that. Let's put in some number 7s. So this is a better approach. We should number carbon 7 consistently in all of the pictures. And furthermore, it would probably be best to also give a new number to this carbon that we're using in the base. So let's call this carbon 8. And let's number that consistently in all of our pictures as well, carbon 8. Beginning students make the fewest mistakes if they make an effort to consistently number all their carbons in all their pictures. Please pause the video and try this problem. Now let's discuss the solution. We can start by numbering all the carbons. It's difficult to number these carbons because these are 3 separate methyl groups, so I guess I won't number those. There are no ionic bonds. Phosphorus is a nonmetal bonded to other nonmetals here. So these are covalent bonds, no ionic bonds, so there's no formal charges that we need to draw in. Nobody here has a negative formal charge, so we're going to have to use a neutral nucleophile. We can use the phosphorus as our neutral nucleophile because the phosphorus has a lone pair. We've learned that we can use a neutral atom with a lone pair as a nucleophile. And notice that phosphorus is specifically included on this list of a neutral atom that can act like a nucleophile because it has a lone pair. You should probably memorize this list of 4 atoms, oxygen, nitrogen, sulfur, and phosphorus, that are commonly used as neutral nucleophiles because of their lone pairs. Now we look for a leaving group. Well, we know that neutral chlorine can be used as a leaving group. Now, what about neutral fluorine? Is neutral fluorine an acceptable leaving group? Well, remember that neutral atoms are usually not acceptable leaving groups unless we've specifically learned otherwise. We've specifically learned that neutral chlorine, bromine, and iodide are good leaving groups. We've specifically learned that neutral sulfonates are good leaving groups. But what about neutral fluorine? We haven't learned anything specifically to tell us that that's a good leaving group, so no. We should assume here that neutral fluorine is not an acceptable leaving group. Neutral atoms are usually not acceptable leaving groups, unless you specifically learn otherwise. Neutral fluorine is in the same column of the periodic table as neutral chlorine, bromine, and iodide. Nevertheless, neutral chlorine, bromine, and iodide are good leaving groups, and neutral fluorine is not an acceptable leaving group. So that answers our question. We are not going to use the neutral fluorine as the leaving group. We'll use the neutral chlorine. Therefore, our alpha carbon won't be carbon 3. The alpha carbon will be carbon 4. Now we can choose a mechanism. We'll have to use our table to choose a mechanism. First, we have to notice that carbon 4 is a primary alpha carbon, and now we can use our table. We have a primary alpha carbon, which puts us in the top row of the table. Our nucleophile is neutral phosphorus. Here's neutral phosphorus in the middle column of the table. Middle column and top row puts us in this cell of the table, so we predict that the mechanism will be SN2. Remember that on the exam, you'll have to keep switching gears between different mechanisms. So you can't assume that all the mechanisms are SN1. You have to use the table to determine the mechanism, or use other information sometimes in the problem to determine the mechanism. Let's again consider this fluorine. Could we use the fluorine as the leaving group for the mechanism? Well, remember that both an SN1 reaction and an SN2 reaction require a good leaving group, because the leaving group participates in the rate determining step for both SN2 and SN1. But we know that fluorine is not a good leaving group. Therefore, no, we cannot use the fluorine as the leaving group for this reaction, and therefore we cannot use carbon 3 as the alpha carbon for this reaction. On the other hand, chlorine is a good leaving group. So we use the chlorine as the leaving group for the reaction, and we use carbon 4 as the alpha carbon for the reaction. Why was the fluorine included in this molecule? Basically just to distract us. It's not going to play any significant role in the reaction. So now we're ready to draw our mechanism. Now remember that the mechanism for an SN2 is a one-step mechanism where the nucleophile attacks the alpha carbon and the leaving group leaves the alpha carbon simultaneously. In SN2, the nucleophile attacks the alpha carbon and the leaving group leaves the alpha carbon simultaneously in the same step. Now we can draw the product from that step. Here's our product. Now the phosphorus is covalently bonded to these methyl groups, and there's no arrow telling us to break the bond to the methyl groups, so make sure the phosphorus is still bonded to all three of these methyl groups in the product. Most importantly, we have to change this charge. Remember, we always change two charges for every step. So we're changing the charge for the phosphorus at the beginning of the electron-pushing arrow series and the chlorine at the end of the electron-pushing arrow series. Since the phosphorus started neutral and it lost electrons, the phosphorus should change to a positive formal charge. The most common mistake that students make is leaving off this positive formal charge. But if you leave off the positive formal charge, your answer is completely wrong, because the most important thing to get right about the products is the formal charge. Now, is this reaction finished, or do we need another step? Well, usually we would expect that when there's a formal charge on our main product, we would usually expect that the mechanism is not finished. But we need to learn that SN2 reactions are an exception to that. Most professors would consider that it's okay for your final answer for an SN2 reaction using a neutral nucleophile to end up with a positive formal charge. So here we'll follow this exception. This was an SN2 reaction where it's okay to end up with a formal charge on our main product. So this is the final product of this reaction. And what most professors like to do here is most professors like to draw the chloride close to the phosphorus to show an ionic bond between the negative chloride and the positive phosphorus in the products. Let's see. Well, for completeness, let's mention that carbon 4 is delta positive because it's attached to the chlorine, which means that carbon 4 was our electrophile. It's good to really label all the roles that all the atoms are playing and identify the clues that each atom plays that role, just so that you're building your Ochem skills. Notice that we don't make any changes to the configuration at carbon 3. Carbon 3 is a stereocenter, but it's not being inverted by this SN2 reaction. SN2 inverts the configuration at the alpha carbon, but not at other carbons. So since this carbon was not participating in the reaction, there was no reason for its configuration to change. And of course, our actual alpha carbon, carbon 4, is not a stereocenter. Since carbon 4 is not a stereocenter, it would be meaningless to try to invert the configuration at carbon 4. So the main purpose of this problem was to show you that just like SN1, SN2 requires a good leaving group. So if there's something like fluorine in the molecule, we cannot use that as the leaving group for either SN2 or SN1. As it turned out, we just ended up ignoring this fluorine for this SN2 reaction. Just like on the previous problem, we couldn't use this neutral oxygen as the leaving group for SN1, so we pretty much just ended up ignoring this neutral oxygen in this SN1 reaction. Both SN1 and SN2 require good leaving groups because the leaving group participates in the rate determining step for both SN1 and SN2. So if you see a neutral atom that you haven't learned is an acceptable leaving group, then you can't use that as the leaving group, either for SN1 or for SN2. That's the lesson from our last two problems. This problem also gave us a chance to get a little bit more practice with an SN2 reaction with a neutral nucleophile. Compare that with SN1 with a neutral nucleophile. When we do an SN1 reaction with a neutral nucleophile, the neutral nucleophile ends up with a positive formal charge, and then we do an acid-base cleanup to get rid of that positive formal charge. That's the normal pattern that you will usually encounter in other Ochem reactions. But SN2 reactions are an exception to that normal pattern. When you do a SN2 reaction with a neutral nucleophile, it also ends up with a positive formal charge, but then most professors usually would just leave that positive formal charge in the final product for the SN2 reaction. Mechanisms are usually not finished when the main product still has a formal charge, but SN2 reactions are an exception to that pattern. Let's try a review quiz. Please pause the video and answer these questions. I hope that you actually really did try these problems. It would be good to write these definitions down on paper. Here's the answer. You should have known that the 5 roles are nucleophile, electrophile, leaving group, acid, and base. And I hope that you attempted to give 2-part definitions for each role. It's not good enough to say that a nucleophile donates electrons. You have to say that the nucleophile donates electrons to join an electrophile. Otherwise, you can't tell the difference between a nucleophile and a base, because they both donate electrons. Again, give 2-part definitions. It's not good enough to say that an acid gives away a proton. You also need to know what it's doing with its electrons. So you need to know that an acid receives electrons and gives away a proton. And I guess in a way, most of these are 3-part definitions because the definition also includes what that role reacts with. You should know that nucleophiles react with electrophiles and that bases react with acids. So I hope that you're trying to learn these definitions pretty much word for word, because these are the most useful ways to think about the definitions of these roles in Ochem. Your success in organic chemistry absolutely depends on having complete mastery of these roles and these definitions. So keep reviewing these roles and these definitions however many times is necessary to make sure that you have complete mastery of these definitions. These roles will be fundamental to your success throughout both semesters of your organic chemistry class. Remember that one way to improve your skill with these roles is you should be trying to identify and think about these roles for pretty much every organic chemistry problem. For this problem, for example, we were careful to identify the nucleophile, the leaving group, the electrophile, the acid, and the base for each step. And I hope that you're trying to carry that out for every mechanism that you carry out now. Try to identify all the roles that are participating in each step. I know it might feel like that's going to slow you down, but that's an important tool for getting the mechanism correct. And if you keep practicing that skill, you'll get much better mastery of the meanings of those 5 terms. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.